Good. Okay. Hi, my name is Rick Pardo. I am here today wearing my Smarter Science smock. I'm actually a teacher from the Thames Valley District School Board, working as a learning coordinator now. I got into teaching about 10 years ago. Previously I was working as a scientist with physical medicine and rehabilitation department at a university, and part of my job there was to work with third-year medical students and help them design their own experiments. And what we found is they had a lot of challenges around how to sort out variables they were looking at, like the control variables, independent, dependent, and I really enjoyed working with them, but was thinking that this is pretty much the cream of the crop that we have academically, and if they're struggling with these concepts, that we really need to get to them before third-year medical school. What's the rest of the population doing in terms of scientific literacy? So I made the decision to go into teaching. I went to Teachers College and became a physics teacher and taught general science for 10 years. And so these posters, and the Smarter Science process is our way of making the invisible visible. And by invisible, I mean that thought process, those habits of mind that scientists just take for granted when they're walking through and trying to solve a problem or design an experiment, and taking that inside thinking process and putting it out to make it obvious for kids to go through that process. Okay? So you want to show you an example? Or is that good? Example? Okay. So what we're moving towards is a way for people of various experiences to be able to teach this. We have science teachers that understand independent, dependent, variable, have been teaching science a long time, are very comfortable with it. We also have elementary teachers who are wonderful people, bright people, but haven't seen science since they themselves were maybe in grade 10. And now they have to teach their own science. So how do we make that, how do we help everybody get through that? So we're using what is called DRIVE, D-R-I-V-E, but DRIVE. So demonstrate, replicate, and then variate. So the idea would be to be very obvious in your demonstration of any experiment, and warn with the challenge to the kids that they're going to have to replicate what you've done right away. So let's say we say something simple as one of those paper gyrocopters that you drop and you watch it fall. It falls like a maple key. Okay, so you would ask the students to watch what you do, and you very meticulously fold the paper, add the paper clip, fold out the wings, and drop the gyrocopter. We ask them to say, put one color post-it note. That is what the scientist does, so the folding and the adding the paper clips. So let's say they go on yellow, and then what actually happens to the gyrocopter when it's released goes on the pink. So we make the distinction in the observations, what the scientist does versus what happens to the object or the situation. And what we have over here, so you'd end up with yellow post-its, and the color cue is to get kids to change their mind. So here's what the scientist does. We're wondering why they're doing that, and then here's what we actually saw happen, pink. All right? So we pick one of those things. So it might be the time that it takes for the gyrocopter to fall, and we say we're going to focus our attention on that. That's a possible dependent variable. The thing that the behavior that the scientist decides to focus their attention on is what's called the dependent variable. So that one thing. So now, students, you need to get your gyrocopter to behave the same way as mine, and I want you to figure out the time it takes to fall. And then you're going to record that. And once we get the entire class to agree on the protocol so that all have the same gyrocopter falling at the same time, and we accept a range of numbers, we have our control set of data from the class, we accept a range of numbers as opposed to a single fall time, then we're ready to move to the next step, which is, okay, now that you've had your hands on it and see how difficult it might be to get the gyrocopter to fall at the same time, what could we do to alter that? So what is it that the scientist did that may change the way the object falls? Okay, so we move these things over, right? We could make the wings longer. We could add more paper clips. We could change the type of paper we're using. We could drop it from a different height. All these things may affect the amount of time that the gyrocopter takes to fall. The next set of posters, then we move to the next page, which is Okay, we move from the green box to the green box, the dependent variable, and we pick one of these things. Let's say it's the wing length. We want to change the length of the wings. So one variable I will change will be the length of the wings, and we're going to see how that has an effect on the fall time of the gyrocopter. All these other things we've already brainstormed as a class what could possibly affect that. They have to come with us. We have to control them. We can't change those other things. So the same number of paper clips, same number of paper, same length of the body, all those things have to stay the same drop height, right? The last one, the last poster in this series has some writing stems in it. So it gets the kids to start talking in terms of the if-then statements, those protocols. So if we change the length of the wings, what will happen to the time the gyrocopter takes to fall compared to our control? Right? So you get that they got the right. They can generate their own question, and then what is my hypothesis? So based on my question, I predict that if we make the wings longer, then the time that the object falls will be less or more. But they make a prediction, right? And we try to get them to not sit on the fence with them when they make their prediction. The better way is to get if we increase the wing length by 20%, then the fall time will increase by 20%. And we separate the prediction statement from the rationale, which is, then they talk about, I think this will happen because. So again, it allows the teacher to differentiate and to offer support to the students. If they can't formulate a proper prediction statement, they're going to have trouble with the rationale. We've got some people that know the science behind air turbulence and aerodynamics and that sort of thing, but they can't formulate a prediction statement. So it allows the teacher, again, to customize the education and the support to the kids. Once they've done this and they can understand this, the next step is we ask them to generate their own data collection table. Once that's approved by the teacher, they're good to go. Right? If they can articulate their question, come up with a prediction statement, generate a data collection table, they're good to go. This allows us to do things like have every science pair working on a different experiment, right? So they can all generate their own experiments and come to their own studies. Okay?